This is the last lecture or talk about chapter 14 and about solutions. This particular application has to do with medicine. When somebody is dehydrated, or sometimes they're having trouble eating, or they need specialized medicine that is dissolved in a solvent like water, it can be delivered to them intravenously into the veins. And you've seen these bags before in movies and in hospitals. And you can't just put the medicine or put some water or put some glucose for energy straight into the vessels. You actually have to make the concentration of whatever it is you're going to administer have the same concentration as the concentration of blood. Since we're talking about colligative properties, what's important here is that the number of particles per kilogram of solvent is the same going in as the blood already has. We would call that kind of solution isoosmotic, or simply isotonic. Maybe you've heard of tonic water. Tonic water is a water that has stuff dissolved in it, like carbon dioxide. It's often used to mix with other things. Now, the reason the solution has to be isotonic is because of the fact that whenever you have a membrane, like a cell membrane, whatever is more concentrated on one side of that membrane will try to diffuse through the membrane to go to the other side, which is less concentrated. Now, that membrane is going to have a certain size of pore. Its porosity is going to depend upon how big the openings are and whether or not the particles then can get through those openings. Large particles, let's say proteins and sugar molecules and so forth, are often too big to get through small holes, whereas little particles, like small ions or water molecules, often can easily get through the openings or holes in a membrane. Excuse me. And so if we were to have a hypertonic solution down here, hypertonic means that it's a high concentration. And if you have a high concentration of salts outside the red blood cells, the high concentration stuff may not be able to get in because it's too big. Meanwhile, the higher concentration of water, which is inside the red blood cells, can get out. So instead of increasing the concentration in the red blood cell, you are trying to decrease the concentration of the water outside the red blood cell or the living cell. That's pictured right here. You have a net flow of water out. And as that water flows out, the cell is going to shrivel up. And that process of shriveling up is called crenation. Now, the opposite of that is if you have a hypotonic solution. Hypo means not enough. The opposite of hyper, which is too much. Hypotonic would be a very, very dilute solution. So whatever the particles are dissolved in the water outside the cell, that concentration is smaller than all the stuff that's dissolved inside the cell or the red blood cell. These look like red blood cells because they're bioconcave discs, and that shape is typical of red blood cells. It is a way of maximizing the surface area of the red blood cell for the sake of gas exchange and delivery of oxygen. Meanwhile, hypotonic means that you have a higher concentration of water outside the cell and a lower concentration of water inside. Or another way of saying it is that inside the cell you have lots and lots of particles like proteins that have been made by the DNA, which would not be true of red blood cells because red blood cells don't have a nucleus, therefore they don't have DNA, therefore they don't make proteins. But there are other things inside the red blood cell, hemoglobin molecules. So the stuff inside the red blood cell can't get out, but the water can easily diffuse in. So if you can't make the outside of the cell more concentrated with your particles, you can make the inside of the cell less concentrated by water diffusing in. And so you have a net flow of water in. That's going to cause the cell to swell up. Plant cells, because they have an additional cell wall, are somewhat protected against this, and that's a good thing, thinking of all the plants that need to be able to survive either in shallow water or sometimes even be able to survive the periodic flood. But animal cells don't have that cell wall. And consequently, when animal cells and human cells inflate with water, as a result of that inflation, they burst as the water comes in. That's called to lyse. When a cell bursts, that bursting of the cell is called lysing. If it's a red blood cell, we call it hemolysis, hemolysing, and it kills the cell. Now we're going to pick up with colligative properties, looking at it from another angle. And this is, what about the colligative properties of solutions that contain ions? All the examples in the chapter so far have used non-ionic solutes. They might be biological, they might be inorganic, but they're non-ionic. Well, what about dissolving ionic compounds in water? We do that all the time, especially in the wintertime. We like to put salt on snow or icy roads and sidewalks. And as the sun shines on the snow, that salt begins to work its way in the melted water and then begin to work its way down through the salt. And then in the process, what happens is it interferes with the freezing process. Remember, adding solutes to a solvent depresses the freezing point. It interferes with the ability to crystallize or become a solid. Now, in the case of an ionic compound like sodium chloride, it breaks up into two ions because sodium chloride is so soluble. So if I had a 1 molar solution of sodium chloride salt in water, I could also say I have a 1 molar solution of sodium ions and a 1 molar solution of chloride ions. Now, a 1 molar solution would actually be very, very concentrated, and we often would be talking about something more dilute than that, like a 10th molar solution. And 10th molar for that matter. But what you're supposed to see here is my 1 sodium chloride becomes 2 separate particles in water. And that therefore doubles the effect of the colligative property. It will double the freezing point depression, that is the delta T, in which the freezing point is lowered. It'll double the boiling point. It can double the vapor pressure of a evaporated solvent in a closed container. It can double the effect of the osmotic pressure. Now, when we say it doubles it, it's because we form twice as many particles compared to the actual solution that we prepared. Now, that's kind of theoretical, and I'll explain what I mean by being theoretical in a minute. If we take a look at this chart, if sodium chloride should become 2 particles, we would expect that when we dissolved any concentration of sodium chloride in water, that it would double the colligative property. The freezing point is what this one is talking about. And so we would expect that the ratio of the measured to the calculated, as if we were ignoring sodium chloride, it would double the effect. And you notice that it doesn't quite do that. In fact, you can see a pattern here, that as my concentration gets greater and greater and greater, my colligative the property effect from the ionic compound drifts farther and farther away from the idealistic value of 2. And the reason for that is, as your solution of sodium chloride is more concentrated, becomes more concentrated, those sodium and chloride ions are going to begin to attract each other. There won't be enough water molecules to surround them and hydrate them and keep them separated. And as a result, instead of having twice as many particles, you won't have quite as many as twice as many particles, because some of the sodium and the chloride ions are going to recombine, reducing the number of particles in solution. Let's take a look at sodium sulfate. If I were to ask you right now in class, how many ions does that make? Hopefully you would say 3, 2 sodiums and 1 sulfate. I hope you would not say 7, 2 sodiums, a sulfur, and 4 oxygens. That would not be true. You get 3 ions here. You would get 2 sodium ions, and you would get 1 sulfate ion. So you would expect that the impact that sodium sulfate, if you were to dissolve it into water, would be a factor of 3 times the colligative property, 3 times the freezing point depression, 3 times the boiling point elevation, and so forth. But it's not quite that exactly 3. As your concentration gets bigger and bigger, you'll notice that, you'll notice that the ratio of the measured compared to the calculated is ignoring the fact that it's an ionic compound, drifts farther and farther away from 3. Now this ratio here is called the Van't Hoff factor. And the Van't Hoff factor is named after a Dutchman who happened to be the first recipient of the Nobel Prize in Chemistry, way back when the Nobel Prizes began to be awarded about the turn of the century, from the 19th into the 20th century. And the way that you calculate that Van't Hoff factor is you use the equation that your change in freezing point, to use the freezing point as an example, is simply going to be the freezing point constant times the molality. And you can find your delta T. That's your calculated value. But then if you actually did the experiment and measured the change in the freezing point, that number turns out to be greater than the calculated value. Theoretically, that number, that ratio, would be a whole number if the solution were very, very, very dilute. Maybe a 1,000th molality or less. And you would get a 2 for sodium chloride and a 3 for sodium sulfate and so forth. But the more concentrated your molality, the farther away you are from that particular whole number, as the chart at the top of the page indicated. So we use the letter I for the Van't Hoff factor. And unless you are told otherwise and you're doing a test question or a homework problem, and you notice that your solute is an ionic compound, and that's all that you're told, I would use a whole number here, a 1 or a 2 or a 3, depending upon how many ions are in the formula. But then you should realize that it's unlikely to be, and I shouldn't say 1 here, it's unlikely to be 2 or 3 or 4, but slightly less than that depending upon the concentration of the solution, because some of the ions, being oppositely charged, will attract and stay together. So to review, our colligative properties include lowering the vapor pressure, because not as much vapor will be able to escape from the liquid state if particles are in the way. It means to elevate the boiling point, because it's going to take a higher temperature in order to get the solvent particles to escape and boil away. It's going to depress the freezing point like the vapor pressure, because those particles are going to interfere with the solution's ability to freeze. And it's going to make your osmotic pressure larger for electrolytes than for non-electrolytes. Remember, electrolytes are substances that can conduct solutions that can conduct electricity. An electrolyte is the substance that you put into the solvent, water for example, that enables the solution to conduct electricity. We call it an electrolyte if the resulting solution can conduct electricity. You might recall in honors chemistry, you perhaps did a lab on conductivity of maybe 25 different solutions, some of which were electrolytes and some of which were not, some of which were good electrolytes and some of which were mediocre electrolytes. And again, here is the reason why you don't actually get the whole number. Some of the oppositely charged particles recombine to make larger clusters or particles, and that contribute to the interference of that colligative property, the reducing of the effect of the critical colligative property. So here's a problem. We have a relatively dilute solution, and notice the word aqueous here. It's easy to miss that. I've had students come up and say, what's the solvent in this problem? Well, of course, the solvent is, and I hope you're saying it out loud, if it's aqueous, it's water. And in this problem, we're told the temperature at which the solution freezes. And you might recall the lab that you did just recently, probably. And in that lab, you put a solute into solvent and dissolved it, and then you cooled it down to see when it would begin to crystallize in order to find what the new freezing point was, so you could calculate the change in the freezing point. So our first strategy is to find out what is that change in freezing point. And so we need the constant for our solvent, which is water. Don't go looking for the constant for something else. For example, antifreeze or something like that. And then here is my molality of the solution. And we find out that my delta T is this. And since we're talking about a freezing point, the negative sign means it's going to be depressed. And that value goes right there. Now, this value, which is the measured freezing point, change in freezing point, is that. Now remember, the true freezing point of pure water is 0. So we don't actually have to do the new freezing point minus the original freezing point, which is 0, or vice versa. If we had a different solvent that has a different freezing point than 0 degrees Celsius, then you'd have to do the subtraction to find your delta T. Notice my colligative property is not exactly 2. And that's because my original concentration is 200ths molality, which for colligative properties is relatively concentrated. Now, most of you are familiar with true homogeneous mixtures that we call solutions. Homogeneous means you can't see the individual components of the mixture. In other words, they're in a single phase. Usually that single phase is a liquid. And you are familiar with suspensions. If you were to take some water from the Mississippi or Merrimack or Missouri rivers, for example, there'd probably be a lot of sediment floating around in it, and it would gradually settle out. In other words, as long as that water is moving or shaken, it's suspended in solution. But if it becomes quiet and settles, and still, I should say, then the stuff settles out. You might notice on a river, if you're canoeing one of the rivers, the smaller rivers in Missouri, when you go around a bend, let's say, through a place where the water is moving rapidly and suddenly it turns a corner and the water gets a little shallow and then it becomes very calm, you will often find a sandbank or a gravel bed off to the side. And that's because a lot of the sand and gravel that's been swept up by the moving water and suspended for a while the water is moving quickly, it settles out and creates that bed or sandbar. Now, colloidal dispersions are in between. A colloid is something in between a solution and a suspension. The particles are too big to be considered a true solution, but they're small enough that they can be juggled, if you will, in the solution pretty indefinitely, and they don't really settle out. And the word colloid comes from that old Greek word, Kolla, which is where the person who first investigated this, the British chemist Thomas Graham, that's how he came up with the name. Most of the people in sciences back then, as well as in literature, if you went to Oxford or Cambridge, major universities, you'd be expected to know some Greek and Latin. Now, some of the properties of colloids. They have 2 very distinguishing characteristics. They generally have very high molar masses. For example, proteins and hemoglobin would have molar masses in the thousands and tens of thousands. The second characteristic is that these particles are relatively large, about 1,000 nanometers. Suspended particles would be bigger than that. And true particles in solution, particles in a true solution, would be much, much smaller than 1,000 nanometers. If you were to shine light through a colloid, you would see the Tyndall effect, the scattering of light as the light passes through and bounces off those particles, even if you can't actually see the particles with the unaided eye as you're looking at the container. And then the third property is that because they are in the middle, not so large, generally they can remain suspended for a very, very long time so that they don't settle out. Now, some of the vocabulary words that surround this is the word sol, and that's going to be a solid that's dissolved in a liquid. The word gel, which is going to be, and I shouldn't have used the word solenoid, suspended or dispersed in. The word gel, you recognize that in the popular salad or dessert called Jell-O. Colloidal dispersions also have a huge surface area, and we'll talk about the effect of that in a little bit. But that surface area for a sphere of about 200 nanometers could equal the size of several football fields. That's an awful lot of surface area. But let's take a look at this chart. So notice the vocabulary words, the dispersing medium and the dispersed medium or phase. The dispersed phase is kind of like the solute, but we save the word solute for that which is dissolved in the true sense of the word dissolving. And the dispersing medium is like the solvent, but we don't use the word solvent. And so if we disperse a liquid in a gas, we have an aerosol. If we disperse a solid in a gas, we have an aerosol. You can even disperse a gas in a gas. You can also disperse a gas in a liquid. We call that a foam. And of course, shaving creams, whipped cream, marshmallows are examples of that. You can disperse a liquid in a liquid. Call that an emulsion. Mayonnaise, milk, face creams. You can disperse a liquid in a solid, and there's your Jell-O, cheese, butter, jelly. You can disperse a solid in a liquid. That's called a sol. Milk of magnesia, for people who have an upset stomach, that would be an example. And you can even disperse a solid in a solid. Sometimes that requires heating the solids up a little bit to help them to mix in each other. You won't come across that very much. By the way, a milk glass is not a glass of milk. Now, these colloids, containing dispersed materials in a dispersing medium, can be considered hydrophobic and hydrophilic. Hydro, of course, refers to water. Phobic, you might recognize the word phobia, to be afraid of or scared of or repulsed by. And philic, think of the city Philadelphia, which supposedly is a city of brotherly love. If the Cardinals are playing the Phillies, you don't see a whole lot of that. But it comes from the Greek word phileo, which is the word for brotherly love, as opposed to some of the other Greek words for love, like agape. Now, some of these molecules then can be so large that one end, in a sense, doesn't know what the other end is like. The molecule's so spread out. You can have a molecule that is so big that one end is hydrophobic and the other end is hydrophilic. And that becomes very important because of the fact that when it comes to I want to make sure I didn't skip a page here. When it comes to washing dishes that might have oil or grease on them, or washing blood stains or grass stains or oil stains out of clothing, it's very helpful to have the kind of molecule that, and we'll just jump ahead a little bit, that is hydrophobic at one end meaning it's nonpolar, and hydrophilic at the other end, meaning it's polar. So this polar end is polar because it has an ion connected to it. Sodium, or in the case of more other detergents, let's say potassium or something. And then this end over here is nonpolar. It's a big, long carbon chain with hydrogens branched off of it. So the polar end will dissolve in the water, and the nonpolar end will dissolve in the grass stain, oil stain, grease stain, or whatever it happens to be. And that's basically how you make your soap molecule. Soap molecule is going to be this big, long chain of carbons, and you can see how many carbons in a row repeat themselves. And then you've got the polar end. Now backing up just a little bit. Soil particles that are being carried down by moving water are often hydrophobic because of the fact that they are nonpolar. Sometimes salt materials can become hydrophilic if they pick up a static charge. But in order to get these soil particles to settle out, we need to add some salts. And of course, by adding salts, you're adding ions, which we can say are very, very, very polar. And by adding those salts, you help to make the soil particles now charged enough to be able to go down the drain with the water, be washed, to settle out of the solution, I should say, so that you can have the pure water. One of the very first summer I was doing research in Idaho, we were bringing up water from down in the aquifer, hundreds of meters below the surface of the ground. And even in the desert, there is water if you drill deep enough. And this water was thought to be absolutely pristine and theoretically uncontaminated by microorganisms or bacteria. Well, we would bring this water up, but of course it would have some soil dissolved or suspended in it, and we would have to flocculate it. Flocculate it would mean add a salt that would cause all of the sediment to settle out very rapidly so we could take the pure water, at least we thought it was pure, put it in a petri dish, and test to see if any bacterial colonies would grow in it. And lo and behold, it turns out that deep under the Earth's surface, there are microorganisms, bacteria that actually live down there, not bacteria from pollution or from the surface, but that's actually, in a sense, their home. And that was a remarkable discovery that our lab participated in making. And I think this is way back in the year about 1992, I think it was. It was the year before the flood in the St. Louis area on the Missouri and Mississippi rivers. Now, sometimes we like to use emulsifying agents such as soap or proteins that can help remove particulate matter from our solutions, or else the emulsifying agent in this case would help to keep the emulsion from becoming spoiled, to maintain the dispersion over time. And that's why salad dressing and mayonnaise and milk can last. Once it's produced, it can last in the store shelves until you open the container and then put it in the refrigerator. And certainly for salad dressings and mayonnaises, even though they put a best if used by date on them, can actually last for years. Milk, not so much. A surfactant then, this has something to do with the surface. And sometimes if you add a surfactant to water, stuff that might be floating on the surface would immediately sink, because it changes that surface tension and in a sense makes it more permeable, if you will, and interferes with those bonds between those the bonds between all the molecules that make up the surface of the solvent. And so here's an example of adding a surfactant. The surfactant is being added right there, and that single drop disrupts the intermolecular forces holding the molecules on the surface together. And then as a result, the material that was resting on the surface because of the surface tension now goes through the solution and eventually settles down to the bottom. Modern day detergents, we would like them to be biodegradable. We don't want them to persist in the environment any longer than necessary. And so we like it when they break down, when it's easy for the solvent that it is in and whatever else might be in the solvent whatever other biological materials might be in there, to break these big molecules apart. And so nowadays, we might use something, for example, like the sulfonate group. It looks like the sulfite ion. Remember the sulfite ion, that's the sulfate ion. Here's the sulfite ion. Well, you'll notice that the sulfonate group has a -1 charge instead of a -2 charge. So one of those charges connects it with the rest of the molecule. And then the other is what connects to a sodium or potassium to create the solid salt, the solid substance, I should say, that you might buy in the store. So these synthetic detergents are not naturally occurring ones, they're ones we make in the lab. The more naturally occurring ones, it's not like you go out and you dig up soap somewhere, but the old-fashioned types of soaps were actually made from ashes from a fireplace, which would have sodium hydroxide in it, and animal fat and alcohol, and would create a precipitate. And that particular soap would be very, very harsh. That kind of soap is sometimes called lye soap. And it would really, really clean. I mean, it'd clean your skin and also remove a couple layers of skin cells along with it. And your fabrics would wear out pretty quickly with that kind of soap. Another thing that has been used in the past is the carboxylate group. And that looks more like this. And remember, the carboxylate would have the hydrogen, but of course, if you take that hydrogen away, you leave a negative charge there when you remove the hydrogen. And that's where we get that symbol there that kind of looks like a carbon dioxide molecule, but it is not. Now, the term hard water. Hard water would be water that has lots of alkali earth metals dissolved in it, such as calcium and magnesium. And a lot of places where you might live, if you have well water, your well water might have lots of these minerals in it, in which case it often could leave a scum called a ring in the bathtub if it sits for a while, or in a toilet. And it would also often leave kind of a scum on dishes when you wash them, or on your clothing. And so oftentimes you would need to purchase a hard water treatment system that would get rid of those metal ions, the calciums and the magnesiums, turning the water into soft water. Soft water simply means without the metal ions. Rain would be an example of soft water. I remember when my family lived, when I was in the beginning part of 8th grade for a few months, or the summer before 8th grade, we lived briefly in Dayton, Ohio, and we had well water, and it was very hard, and we had to have a water softener. Well, that concludes chapter 14.